Next up, we've got Andrew Gitlin from the University of California, Berkeley, who will be telling us about a vertex model for LLT polynomials.
Yeah, thank you for that introduction, Andy. My name is Andrew. I'm from UC Berkeley. I'm going to be talking about a vertex model for LLT polynomials. And this is joint work with Sylvie Corteil, David Keating, and Jeremy Meza. All of us are at UC Berkeley. So before I get too deep into the mathematics, I want to talk about LLT polynomials and where this research fits in. They were first introduced in 1997 by Lascaux, Leclerc, and Thibon. And their original formulation was as a generating function for a semi-standard ribbon tableau where they Q-count a spin statistic. But I'm not going to be talking about ribbon tableau. So the formulation I'm going to be talking about is due to Haglund, Heyman, and Lohr from 2005, where it's a generating function for tuples of semi-standard Young tableau, where you Q-count an inversion statistic. To be more precise, I'm not going to be using that formulation exactly, but rather a tweak where instead of counting inversions, I count co-inversions. So these co-inversion LLT polynomials, what we're going to do is we're going to interpret them in terms of upright lattice paths that are in bijection with that formulation. Okay, so my plan is first I'm going to review a vertex model for Schur polynomials. Then I'm going to introduce a vertex model for the co-inversion LLT polynomials that sort of extends the vertex model for Schur polynomials. And then once we have that vertex model, I'll do stuff with it. I'll sketch the proof of some results about LLT polynomials that are proven using the vertex model framework. Okay, so first let's go over a vertex model for Schur polynomials. Oh, by the way, I'm going to be using French notation. Kyle was using English notation, but in French notation, it's sort of upside down, where the first row is on the bottom. So that's the first row of my tableau. But anyway, there's a well-known bijection between fillings of skew-Young tableau, semi-standard skew-Young tableau, and non-intersecting upright lattice paths, where each row gives me one of the paths. So for instance, this first row corresponds to that lattice path. And the way to think about this is that the filling gives you sort of exiting directions. So namely, this one tells me the first place where the path exits to the right. So that one corresponds to the path going to the right in row 1. This one gives me that. This 3 means that I exit to the right in the 3rd row, and this 5 means I exit to the right in the 5th row. Okay, so we do that for each row of the tableau. The partition lambda gives me the top boundary condition, so it tells me where the path is exiting through the top. And the partition mu is giving me the bottom boundary condition, so it's telling me where the paths are entering through the bottom. Okay. So once I have this configuration of upright lattice paths, I can give each box, each vertex, a weight. Namely, the weight of a box is going to be xi, where I is the row number, if I exit to the right. So these two vertices give me an xi. And the other possible vertices give me a weight of 1. And then the weight of a lattice configuration is just the product of the weights of all the vertices. So in our example, these two boxes give me an x1, these two down there. So that's why I have an x1 squared here. And if you do this out, this is the weight that you end up getting for this lattice configuration. And then the partition function for the vertex model is the sum of the weights of all possible configurations. It's not too hard to see that the weight of a configuration is just x to the t, where t is the corresponding semi-standard Young tableau. So in this case, you end up recovering the skew-Schur function. So our partition function, in fact, equals the Schur polynomial. Okay, so this is a vertex model for the Schur polynomials. And now I'm going to extend this vertex model to LLT polynomials. But before I do that, I should define what LLT polynomials are. So the formula for LLT polynomials looks like the formula for Schur polynomials, but with two differences. One is that I'm defining it for tuples of skew partitions as opposed to just a single skew partition. And the second fact is that I have this t that I have to worry about. So I'm going to t count the number of co-inversions, where a co-inversion is given by a triple ABC, where A and C are adjacent cells in some shape. B is a cell directly underneath A and C in an earlier shape. And A is less than or equal to B is less than or equal to C. So the way to remember this is that it's a triple where as I weakly increase, I go around counterclockwise. So as I go around counterclockwise, A goes to B goes to C, I weakly increase. Okay, so I'm t counting the number of co-inversions, and that gives me the formula for co-inversion LLT polynomials. Okay, if you've seen LLT polynomials before, you've probably worked with the inversion formulation of LLT polynomials, where instead of counting co-inversions, you count inversions, an inversion just being a triple that isn't a co-inversion triple. But the two are related just by messing around with the powers of t. So everything I do for the rest of the talk is going to be about co-inversion LLT polynomials, but the results can be translated to be in terms of inversion LLT polynomials just by messing around with the powers of t. Okay, so when I set t equals 1, I end up recovering a product of skew Schur polynomials. And so this actually suggests a place where we can start if we want to find a vertex model for LLT polynomials. Namely, each shape gives me a set of paths. So I'm going to assign a different color to each of the shapes and superimpose those paths. So in this example, blue is color 1, it corresponds to the first skew shape. Red is color 2, it corresponds to the second skew shape. And I take the two lattice paths or the two sets of lattice paths and just put them on top of each other. Okay, so if I just have one color, my vertex model is going to be the same as it was for the Schur polynomials. Namely, I pick up an x anytime that I exit to the right, and I pick up a 1 otherwise. Okay, but if I have to worry about t, if I have more than one shape, I have to worry about t. And what you do is instead of picking up an x when you exit to the right, you pick up an x times t to the delta, where delta is the number of colors greater than that color that appear in the vertex. So let's see an example of this with two colors. So here, blue is color 1, red is going to be color 2. And just to pick out two of these vertices, this vertex has a weight of xt because blue is exiting to the right and a larger color, red, is present in the vertex. So I pick up an x times t to the first. And then red doesn't go to the right, so it just gives me a 1. So the overall weight of this vertex is xt times 1, which is xt. For this vertex, blue is exiting to the right and red is present. So I pick up an x times t to the first. And then red is also exiting to the right, but there are no larger colors than red that appear in the vertex. So I just pick up an x. So overall, I get an x squared times t. In our running example, there are 3 vertices that contribute a power of t. So namely these 3, where blue is exiting to the right and red appears in the vertex. So that's why the coefficient is t cubed here. And then the x weights are just found similarly to how we did them for Schur polynomials. Every time you exit to the right, you pick up x sub I, where I is the row number. Okay, so overall, the weight of this lattice configuration is x1 cubed, x squared, x2 squared, x3 squared, t cubed. Okay, so I claim that the partition function for this vertex model is exactly the co-inversion LLT polynomial. And the way to see that is that co-inversion triples are in bijection with things that would give me a power of t in the vertex model. Namely, if I have a co-inversion triple ABC, well, that means that AC appears in some shape. So this A means that red is going to enter the column in row A and exit the column in row C. And this B in an earlier shape means that blue is going to exit that column in row B. And so if B is between A and C, then that means there will be some vertex in that column where blue is exiting to the right and red appears. So that's exactly what will give me a power of t when I compute the weight of the configuration. Okay, and so what that means is that the partition function for this vertex model is exactly the LLT polynomial. Okay, so now that we have this vertex model, let's prove some things with it. The first thing is that this vertex model ends up being Yang-Baxter integrable. So it satisfies the Yang-Baxter equation, which you can think of as a sort of commutation relation in the presence of this special R matrix, which I denote with a new type of vertex, which is a sort of cross. Okay, what is this cross? So this cross has weights given by these things. And when there's more than one color, I just replace an x with x times t to the delta, where delta is the number of colors greater than that color of type 1. So the number of larger colors that go diagonally down. Okay, so in the presence of this special R matrix, we can say that the vertices we had before commute with each other. So I'm not going to prove the Yang-Baxter equation for you here because the proof is a pretty complicated induction argument on the number of colors. But just to give you a sense of the sorts of things that you have to check. So the Yang-Baxter equation holds for all choices of boundary conditions. Here I'm choosing the boundary conditions where blue enters here and exits here, and red enters here and exits here somehow. So on the left-hand side, there's only one possible configuration, and it happens to have a weight of x squared t times 1 minus y over x. But on the right-hand side, there are two possible configurations with those boundary conditions. And it turns out that if you add those two up, you'll get the weight of the configuration on the left-hand side. So in this particular case, the Yang-Baxter equation holds, and it ends up holding true in general. Okay, once we have the Yang-Baxter equation, we can use it to prove some really useful things. So first of all, the Yang-Baxter equation pretty much immediately gives you that the LLT polynomials are symmetric in the x's. So this argument is often called the train argument. And the idea is that we're going to push the R matrix through the rows of the vertex model. So if I'm interested in swapping xi and xj, if I'm interested in swapping two of the rows in the lattice, I can take an R matrix on the left-hand side and then use the Yang-Baxter equation to just push it through like a train out to the other side. Okay, but there's only one valid configuration for the R matrix where I have zeros on the boundary, namely the whole thing has to be empty. So I have to put zeros over here. And with those conditions, the weight of the R matrix is just 1. So what this ends up giving is this bottom equation where xi and xj are swapped. So this tells me that I can swap xi and xj, so I can swap any two of the variables, which means that the LLT polynomials are symmetric in the x's. Okay, if you do a slightly more complicated version of the train argument, where you have a whole bunch of R matrices on one side that you're pushing through to the other side, you end up getting Cauchy identity for the LLT polynomials. So I'm not going to go over the proof here, but as I said, it does come down to the train argument, where you have a bunch of R matrices on the sides, and these gray vertices are slightly modified versions of our original vertices. Okay, and that's all I have. So thank you all for listening, and if you have any questions, feel free to ask them.
Okay, let's thank Andrew. Okay, any questions for our speaker?
I had a question related to the description of the LLT polynomials. I was just wondering, because you say you have tuples of tableaus. Is it really tuples of tableaus of shape lambda over mu, or is it kind of the ribbon tableaus that are given by those skew shapes?
Yeah, so it's tuples of skew tableaus. And not all the tableaus have to be the same shape. So for instance, like in this example, this is the first shape is 2, 2, and the second shape is 2, 1.
Okay. All right. And can you just go back to the one where you had the lattice path? Just wanting to look at it. I think the earlier one. Yeah, that one. Yeah, just wanted to have a look at it.
Okay.
While you answer other questions.
It looks like there are 2 questions in the chat. Would you like me to read them?
Yeah, I can see the chat. So why is co-inversion an interesting or helpful statistic to keep track of? I don't really have a good answer for this, other than it's the statistic that gives the LLT polynomials. Or I should say that inversions give the original definition of LLT polynomials, and then co-inversions are sort of a natural dual to those. Yeah, but I don't really have a good answer other than they give you LLT polynomials.
Okay, other questions?
Oh, I see another question in the chat. How does your lattice model differ from the lattice model for LLT polynomials by Kern, Wolf, and Zhang? I'm actually not familiar with their work. So I can't really answer that question. There's another question in chat that says co-inversions come up in HHL's combinatorial formula for Macdonald polynomials. Yeah, so one of the most famous uses for LLT polynomials was proving the Macdonald positivity conjecture, which is a famous result about expanding the Macdonald polynomials in terms of Schur polynomials. Okay.
Okay, any more questions? We have about 1 more minute for questions if we have any. Okay, let's thank our speaker again.